Welcome to our lecture on energy storage. Today we will talk about the second part, chemical and electrical types of storage. We start with chemical storage, hydrogen storage, and then we will switch over to power to gas, in particular methane. Let's just take a look at the different storage technology and the capacities and discharge times. So we see here the storage capacity on the x-axis and the discharge time on the y-axis. What we discussed already has been the pumped hydro storage, as a mechanical storage. Here in blue color, it is available in the vicinity of 100 megawatt hours to about 10 gigawatt hours of storage capacity, and within this typical discharge time of a day or several days or up to weeks, or if you discharge it quickly, it could be several hours, as we saw in the Goldestal plant, which has if it works on full power, a discharge time of 8 hours. Then we also discussed here in green color the CAES, the compressed air energy storage, which is available at a bit lower values. And also at the very end we discussed about we saw a movie about flywheels, which is only available with relatively short capacities and also relatively short discharge times. What we'll discuss today is first in light green color, the hydrogen storage. Then we will switch over to methane storage, a substitute natural gas in dark gray color, which is available in the terawatt range, and also it can last for several months, up to a year of storage. Then we will go over to the battery types of storage, which is available in the range up to 10-20 megawatt hours, and usually it's applied in discharge time of a day or of several hours. But let's go first for hydrogen storage. The principle is you apply a electrical potential of at least 1.23 volts on two electrodes immersed in water, and it results in the formation of oxygen in the positive electrode and on hydrogen in the negative electrode. The storage of gases, or if you cool it down, liquid hydrogen, is similar to the natural gas storage in pressure vessels or possibly in the future in underground salt caverns. When you use hydrogen storage during periods of an energy surplus, the excess part will be converted to hydrogen via electrolysis and then stored. During peak times of consumption, when the actual grid power is insufficient, the stored hydrogen will be converted back into electricity. The chemical reaction of this process is, so we have water first, 2H2O, is converted in 2 H2 molecules and 1 oxygen molecule. So redox reaction, here you see it again. So we have power generation. The excess power we will use as in for electrolysis. We will generate hydrogen, which we'll use usually in the hydrogen network. Usually the oxygen we won't use. It is released to the air. So we can do either PEM electrolyzers or alkaline electrolyzers, efficiency, for example, 73%, but we come to this a bit later. The reaction type we already saw. Let's take a look at the hydrogen use cycle. The hydrogen from the storage or the cavern is supplied to a fuel cell, which will generate electricity via synthesis of hydrogen and oxygen. Usually the oxygen is taken from the air. So we have wind or solar. This is supplied to the electrolyzer. It uses water and supplies hydrogen and releases also oxygen. We supply to the hydrogen network. From the hydrogen network, we convert back hydrogen and oxygen via the fuel cells into electricity. for power generation. The other way around is power storage. We see now a short movie about that.
Welcome to the group exhibit Hydrogen Fuel Cells and Batteries at the Hanover Fair 2017. My name is Muriel Burkas and we're here at the Technical Forum. We're here for the last presentation of today and I'm very much looking forward. It will be about PEM electrolyzers improving transformation costs through intelligent stack design. Please welcome on stage with me Head of R&D of HTEC Systems, Dr. Frank Alibrod.
Thank you very much for the kind introduction. As mentioned, my name is Frank Alibrod. I work for HTEC since more than 2 years now. And I would start by giving you a short introduction into the company HTEC. HTEC is a pretty old company in the field. It was founded in around 1997. And it was involved in some very nice and very challenging products and projects around the field of hydrogen, but now we focused on PEM electrolysis. In 2010, GP Joule integrated HTEC Systems as a subsidiary within the company. We have now 2 offices in Germany. One is located in Lübeck in the north of Germany. The other is located in the south, close to Augsburg in Bavaria. We have one goal at HTEC, and our goal is the most inexpensive conversion of electricity into hydrogen using PEM electrolysis. Our mother company is GP Joule, which is a pretty young company compared to HTEC. It was founded in 2009, but has already 190 employees. GP Joule is a player around the field of renewable energy, with the goal to supply renewable energy around the clock 100%. We have offices in Reusen-Köbel, the head office, very north, in Lübeck, Berlin, Buttenwiesen, and Geislingen an der Steige in the south of Germany, and also international offices in Toronto and in Los Gatos in the United States. So hydrogen is now. This is our new slogan. We often talk that hydrogen is the future, but we think, or we know, it's already the present. It is pretty easy to put hydrogen, if it's produced from renewable energies, directly into the gas grid. That's one opportunity. You can do methanization and use the methane for different purposes. Of course, mobility. We all know the Mirides, the fuel cell cars. You can use it for fuel cells. Of course, there's industrial applications, chemical applications, and what's the future? It's the reconversion into electricity. So the PEM electrolysis cost breakdown, there's one study saying what actually are the cost breaks, the costs for a PEM system and for a PEM stack. On the left-hand side, we see that a stack contributes more than half to a PEM electrolysis system. On the other side, we see the cost breakdown of a PEM electrolysis stack, saying here that we have 51% only for the bipolar plates. That's a European study, the final report, which was announced just a few years ago. Actually, I must be honest, this is not our costs. I'm actually not allowed to give you the costs, but let's say it's not so far away from the truth that we see it. But when we have such a cost breakdown, we can think about what will we do to reduce those costs. Of course, first we ask us what are the most expensive components. If we have identified them, we can of course say, let's reduce the costs on them. Can they be replaced? Do we really need them? Or can we reduce the waste, which is actually a very nice possibility to reduce cost. We talk to all our suppliers, and then we say, okay, what's the best compromise that every supplier has the fewest waste, and by that we can decrease the costs for the entire stack. And of course, there's another possibility to reduce costs is by mass production, thinking from the beginning. Not only think, oh, what's the cheapest way to produce it in 10 or hundreds. Just think from the beginning. Let's produce 10,000. Let's produce 100,000. That's what we need for the future energy system. And of course, if it comes to 10,000 and 100,000, there must be also the possibility to manufacture it by robots. Think about limitations by the suppliers. Can they, if you have a good supplier, but can the supplier also distribute 10 times, 100 times more as he is distributing now? And of course, one challenging point, especially if it comes to PEM electrolysis, is the availability of raw materials. Do we have enough iridium, platinum on the planet? Can it be produced? Can it be mined? And of course, there's also another possibility just by using the overload capability of the stack. So it's pretty easy to have a stack and put 400% on it, then you have very low specific cost, but the lifetime is a disaster. So you have to find an intermediate way. So we did this, and the first result is what we are very proud of, that we are now able to sell a PEM electrolysis stack, the so-called HTEC S-series, with a weighted production of 0.40 to 3.38 kilograms of hydrogen per day. If you want to just have a S30/10, it comes with 1 kilowatt electric power. It's pretty easy to calculate. Each cell of those stacks has 100 watts. The load range is in between 0.2 to 6 kilowatt until 9.4 kilowatts. We have an overload capability of 188%. We are also able to give a mean MTTF, mean time to failure, and we say this is 40,000 hours now. We've done some very intensive testing in the last years with a total testing time of over 100,000 hours. And with our newest design, we didn't have any failure. As well, we didn't see any significant degradation. It was almost zero. Also, what is pretty new this year is our M-series electrolyzer. So we stepped back. We don't sell only stacks. We also sell electrolyzers. This is the ME100/350, and it produces 100 kilogram of hydrogen each day. The maximum power is 350 kilowatts. And in overload, we can also produce 140 kilograms of hydrogen per day. So, and there's one more thing what we offer with this electrolyzers. This is a guarantee of 4 years. So it's called our performance guarantee, and it comes together with a maintenance contract. So if you want to hear any more details about purchasing such an electrolyzer or purchasing a PEM electrolysis stack, our booth is pretty close, C58, and we can give you pricing and everything on the booth. So the data sheets are available as well for both products that we offer, and I would be very happy to introduce you more detailed into our products at our booth. Thank you very much for listening.
Thank you very much for your time and your spontaneous presentation. Are there any questions for him? No? Okay, I think call it a day at the technical forum. As he announced, if you have further questions, go to the booth later on or tomorrow or this week. I hope you enjoyed the technical forum on the first day, and we will start tomorrow at 10 a.m. with the first presentations right here. Okay. Have a good afternoon, evening, and see you tomorrow. Thank you very much.
Thank you. Thank you.
Hydrogen storage, the characteristics and the application. So we want to balance out power deficits or surpluses as a result of forecast errors for wind or solar power, while it can be supplied within a relatively short period of time, so we can achieve quite high sales prices. Hydrogen storage can serve as a long-term storage, thus providing electricity during days without wind and solar irradiance. Hydrogen storage can store a large amount of energy surplus during high wind periods, whereas currently that energy would be lost if wind turbines would be throttled or solar power plants would be throttled. The advantages and disadvantages of hydrogen storage. Substantial advantage of hydrogen storage is its enormous storage capacity resulting from the large chemical binding energy. The energy density of hydrogen storage, including reconversion by gas or steam power plants, is in the vicinity of 163 kilowatt hours per cubic meters, while pumped hydro storage has densities in the vicinity of about 1 kilowatt hour per cubic meter. The big disadvantage of storage electricity via hydrogen is the relatively low efficiency. So it's 40, maybe 50% for compression of 80 bar. If fuel cells are considered for reconversions, the planner should be aware that the major part of fuel cells are prototypes only. Let's take a look at the cost development. First, it's the so-called alkaline electrolyzers. So see here, nowadays it's in the vicinity of 750 euro per kilowatt electrical, and they expected to go below 500, 350, 400 in 2050. Hopefully it will occur much earlier, because at the moment the hydrogen created by electrolyzers is much more expensive than the hydrogen generated via fossil fuels, via steam reformation of fossil fuels. Here the same for PEM electrolyzers. So also today we are in the vicinity a bit below, a bit higher than the alkaline electrolyzers, in the vicinity of 800 euro per kilowatt. And it's also to go down below 500 euro per watt soon. The actual production methods of hydrogen globally. So as I mentioned already, fossil hydrogen by steam reformation of natural gas is in the vicinity of 90.6% of the world production. Also we have a contribution as a byproduct by 7.1%. Electrolysis from the actual energy mix, which is not completely renewable, it contributes to 1.6%, and low carbon hydrogen 0.7% only. And if we purely take renewable hydrogen, At the moment, the so-called green hydrogen only contributes by 0.1%. That's our data sheet. So we can use it as our peak power, control power, efficiency round trip, so conversion to reconversion is in the vicinity of 40%. It's available in the ranges of kilowatt, megawatt. Some prototypes are being under construction in the gigawatt range. The theoretical storage capacity is enormous. If we take old salt caverns, it can go up to 1,300 gigawatt hours. The energy density is 33 kilowatt hours per kilogram. Before we discussed about cubic meters. Then we have the discharge time, could be from seconds till days or weeks or months. The self-discharge rate, there's no significant self-discharge if everything is tight. The specific investment cost is, as you saw in the pictures before, it's quite hard to define. So in the vicinity, we can say we're in the vicinity of 700 euro per kilowatt. Market stage is prototypes, first pilot plants. Now we go over to the conversion to artificial or synthetic methane. Often the expression power to gas is used for that. So we convert carbon monoxide or in particular carbon dioxide into methane. So we have here our atmosphere where we have some content of CO2, which is relatively low. Better if we take the carbon dioxide, for example, directly from a biogas plant. Then we have our created or generated hydrogen, and together with hydrogen and carbon dioxide we form methane, and we have a leftover this oxygen. The efficiency could be up to 80% for the most modern plants. We come to this a bit later. The reaction is we have 4 hydrogen molecules and 1 carbon dioxide molecules, and this forms methane and 2 water molecules. Here we see it again. So we have here the same as before, the electrolysis. We create hydrogen, and together with carbon dioxide in the so-called methanization process, we form CH4, methane, and there's a huge network existing already on natural gas. We can use the tanks, we can use the pipelines, so we don't have any additional investments cost on that side. Here we see the complete cycle of storage, use and reconversion. Same as before, we got solar and wind power. Via electrolysis we form hydrogen, and additionally we have carbon dioxide. In the so-called methanization process we form methane, and we can use the extensive network, which is much larger than the hydrogen network, to store and to distribute the methane, or same as natural gas. Also we can use some parts directly, for example battery electrical vehicles, electricity directly, or we can use fuel cell electrical vehicles which work via hydrogen, or we can use vehicles which may be a combustion engine and use methane. Here we see the different sectors of use. So first, power generation could be solar, wind. What's dominating at the moment, as you saw before, for the hydrogen production is fossils. Then we have the water electrolyzer, we have hydrogen storage. With some of remaining carbon dioxide, we can form natural gas. Then we can distribute the hydrogen via trailer or via hydrogen pipeline. Is to be considered that the molecule of hydrogen is much smaller than the methane molecule, so the pipelines, the valves and everything has to be very tight, and this relates to higher investment costs. Then we have at the end the applications. So we have it for mobility. We can use it also for residential use, for heating and or electrical power supply. For the industry, which is the largest consumer of hydrogen. Here we see it again in the different representations. So we have here, as I mentioned, hydrogen as a raw material for the industry. We have mobility, so we can use it with combustion engines, hydrogen motors, or natural gas, or via fuel cell converted with a much higher efficiency into electricity and then drive electrical vehicle. We can use it for heat supply. We can use it also, as I mentioned, for electricity generation. So we can either convert it via gas turbine with a conversion efficiency in the vicinity of 40%, or here typically 39%, or via combined cycle power plants with a conversion efficiency in the vicinity of 60%. The peak load capability, we have fast start-up times. Formerly about 8 to 10 minutes. Nowadays the fastest can ramp up in 5 minutes only. So we can have a fast response to changes in load or demand. This is an example of a cost calculation from this publication from Applied Energy. So you see here on the graph, the x-axis is a methanization capacity in megawatt. We have a storage capacity because the tanks also cost, and you can find the cost optimum. But you still see even at the optimum, we are here in the vicinity of 128 euro per megawatt hour, or in other words, 12.8 euro cent per kilowatt hour, which is rather expensive. If you know that the photovoltaic power generation is about only a tenth. If you go to Saudi Arabia or to Portugal, only about a tenth of the generation cost, but you have storage included. And this is just a particular calculation, so you'll find the data which has been used here on the left side. Let's compare the hydrogen production versus the methane production. So we have both sides. We have the generation by power and wind considered as 100%. Then we have the power electronics, which usually works quite efficient. So efficiency is 95%. We lose of this total 100% only 5%, both for hydrogen production and the methane production. Then we have the electrolysis, includes all the accessories. There the efficiency is considerably lower than for power electronics, 75%. So we have a loss of initial energy of 23.7%. Same applies also for the power to gas or the methane production. Then we have a step, the methanization, which only occurs at the power to gas process. So we have here an efficiency of 80%, and we have a loss of the total power of 14.2%. Then we come to a stage which is common at both. So we have here compression 98.5%. This is a loss of the total of 1.1%. Same applies for the power to gas process. Then we have the transport, which is rather efficient. So we have only a loss there of 0.3% for both sides on the total. So finally, we have the power to gas for hydrogen. We have 69.9%. For power to gas for methane, we have 56.1% only. This is quite a recent development from 2019, a European research project called HELMETH. They met at the end is for methanization, and they achieved efficiency of 76%, and they hope to get soon towards 80% of conversion from electricity to methane. How does it work? We make optical use of the process heat from methanization to cover heat consumption of the electrolysis. There's applied a high temperature electrolysis, which works at about 800 degrees Celsius and high pressure. So that has a high efficiency. During the electrolysis, the power is used first to decompose water into oxygen and the energy carrier hydrogen. Then hydrogen reacts with carbon dioxide or carbon monoxide to methane, the main constituent of natural gas, and with heat being released. The advantage of methane over hydrogen consists in the fact that it can be fed into the existing natural gas infrastructure without any limitation or further processing. There's also a movie.
Germany is betting on renewable energy. By 2050, 80% of the country's electricity needs are supposed to be supplied by renewables. What happens when the sun isn't shining or the wind isn't blowing? Will the country run into power supply problems? There has to be a way to store energy generated by wind turbines and solar arrays. In huge batteries, perhaps? Researchers are looking at many options. This container houses technology that could provide a solution to the problem of large-scale energy storage. Ulrich Süberbuehler from the Centre for Solar Energy and Hydrogen Research has high hopes for it.
What's innovative is the method. You take the electricity that you can't store and convert it into an energy-rich compound like natural gas. Then you can keep it for long periods of time.
The concept that the researchers are testing here is called power to gas. It works like this. Using electrical power, a chemical process known as electrolysis is set in motion. That breaks down water into its two constituent elements, oxygen and hydrogen. Then, carbon dioxide is added to the free hydrogen. The two react and produce a substance that is used in stoves and power plants all over the world, methane or natural gas. The reactions that create the methane are controlled in a neighbouring building. This chemicals facility is unique because it can be started and stopped quickly, in up to 15 minutes. Conventional chemical plants typically take much longer to gear up and shut down. In converting power to gas, however, operators have to be able to react fast.
When there's too much power in the grid, then you have to turn the plant on quickly. And when there's too little, you have to shut it back down so that there's more electricity available to the grid. Up until now, we haven't been able to meet those challenges. That's why we're working on making the technology able to cope with the demands of the near future.
Even so, around 30% of the generated power is lost in converting electrical energy into chemical energy. That sounds like a lot, but the researchers say it's worth it, since the only alternative is to turn off the turbines and solar arrays when production is too high.
This is a good approach because you can't save the electricity. First, you go to great lengths to produce power with renewable technologies, but when they produce too much, you have to turn them off. This is how we can change that. It's true that there are losses when we turn the energy generated with renewable resources into fuel, which is chemical energy. But at least then it isn't lost completely.
An old gas storage plant still stands in front of the new research facility, a reminder that the infrastructure for transporting and storing methane is already in place. This one could hold many tons of the fuel.
Methane is a fuel that's easy to store, and in Germany we have excellent infrastructure for transporting it. We have huge underground storage reservoirs where we would be able to store large amounts of the gas for months at a time.
In power plants like this one, the stored natural gas can then be burned to produce electricity when it's needed. Modern natural gas power plants are the ideal complement to environmentally friendly energy production, closing the cycle that begins with the conversion of the power into gas. The power-to-gas system would boost the effectiveness of Germany's switch to renewables, because power production would no longer be tied to the vagaries of the wind and sun.
Let's take a look at the costs and the capacity available. First takes a look at the actual electricity consumption in Germany. It's in the vicinity of 600 terawatt hours per year. We have about 70 gigawatt of installed capacity. Usually of this capacity there is not considered wind and solar. It's just only constantly available power. Then we have the storage capacity. So we have a pumped storage and batteries is only amounting presently at 0.07 terawatt hours. So this would reach only for a couple of minutes. If you would use some part of the electrical vehicles, for example, if you have in the future 45 million electrical vehicles, each has a battery of 40 kilowatt hours, and you would allow only for 25% of discharge for this purpose, we would have an electricity capacity of 0.45 terawatt hours. So this would this would lead to a range of 6 hours of the electricity network and the electricity consumption. Gas power, this would have a capacity of 130 terawatt hours. So this would cover 2 months of electricity consumption. The costs, so as I mentioned already, it ranges from 700 to 1,500 euro per kilowatt. If you calculate the energy supply costs, so for thermal use of natural gas is 2 to 3 cents per kilowatt hour of thermal energy, and goes up to 8 euro cent per kilowatt hour for electrical use. So it's relatively expensive, but prices are going down. So the advantages of power to gas, so electricity from renewables is available around the clock. Wind turbines and PV systems must not switch off during time of overproduction. Reduction of CO2 emissions. Grid stabilization. Disadvantages are the high investment costs is in the vicinity of 20 to 30% more than for fossil fuels infrastructure. For example, here this is calculated for the PMA electrolyzers. This contains costly platinum electrodes and so on. The efficiency electricity to electricity is lower than 50%, so numbers of 40%. So that's it from this part. Next chapter will be on batteries. We start with the traditional lead acid battery.